Well, ladies and gentlemen, I think we have a little bit more time to do another example here, a third example today, very quickly. This one involves entropy change for solids or liquids, in compressibles, in other words. So what we have here is we have a lake, a large body of water, a reservoir, if you like, a lake at temperature T lake. The lake temperature is 25 degrees C, and in is thrown two pieces of hot iron and copper. So these pieces of iron or lumps of iron and copper have initial temperature for the copper, Tc1, initial temperature of 80 degrees C for the lump of copper, and the same temperature, 80 degrees C, initial temperature for the lump of iron. So sub C means copper, sub I means iron, and of course the lake temperature is T lake. So 15-degree lake temperature, 80-degree lumps of solids, iron and copper, thrown into the lake. Now, of course, over time, if we wait, eventually the iron and copper will cool down and they'll come to the lake temperature, provided the lake is very large. It's a reservoir. Remember the definition of a reservoir? A reservoir is a system that is such a large extent, that is so big that no matter what the heat interaction, the temperature remains approximately constant. So if we wait long enough, the pieces of copper and iron, so copper and iron, will eventually fall to the lake temperature. So what do we want to find here? We want to find the change in entropy of the copper, the change in entropy of the iron, the change in entropy of the lake water. So the lake water surrounds the iron and copper lumps. So find the change in entropy of the lake, the copper, the iron, and then we're going to find the change in entropy of everything. So everything will be the lake, the two lumps of copper, in other words, the change in entropy of the universe as far as we're concerned. Remember, the universe is everything everywhere, or the environment plus the system. So we're going to figure out what the change in entropy is for the entire lake solid system. In other words, everything everywhere, or the universe. Okay? So let's get started here. Let's get started. Analysis. Let's find the change in entropy of, I don't know, the copper first. So analysis. So copper is a solid. So the entropy change, delta S, I think I have, hold on a minute, I think I have some masses here as well. Let me see if I have mass of the copper. Yes, I forgot to put that down. Let me put that down before I get started. I just realized I'm missing something. So the mass of the copper, let's see here, the mass of the copper is 20 kilograms. And the mass of the iron is 50 kilograms. Okay, so I forgot to put that down. So let's calculate the change in entropy of the copper. Let's do that first. So that's equal to the mass times the change in specific entropy of the copper. And the change in specific entropy of the copper is equal to let's assume constant specific heats. So it's CV ln T2 over T1, and this is for the copper. T copper 2 over T copper 1. Okay. Now, we got the mass, we got the initial and final temperatures. Check, check. Specific heat for the copper. Remember I was telling you last time, the reason for the difference between the value of Cp and Cv is the presence of boundary work. So when you have heat capacity at constant volume, there's no boundary work over the process. And when you have heat capacity or specific heat at constant pressure, Cp, there is boundary work. Now, if we've got a solid or liquid or an incompressible, then Cp and Cv are the same value. So I can simply say this is Cp, and I'm going to write here, this is for the copper. It can be Cp or Cv, all right? They're the same for a solid or a liquid. Now, we don't have specific heat for the copper. Certainly, it's not given, but let's have a look in the textbook here. Let's have a look in the notes. Let's see here. Whoops. Let's have a look in the notes, see if we can find specific heats for so let's go to the appendix and see if we can find a table containing specific heats for solids or liquids. Here we go. Thermal physical properties of selected solids and liquids. Selected solids evaluated at 300 degrees Kelvin, approximately room temperature. Specific heats, building materials, saturated liquids. So we have iron here. I don't have copper, so I'm going to give you the copper. Iron is 0.48. So let me write here, down here, assumptions. So specific heat says Cp, but it's also Cv. Specific heat for iron is 0.48 kilojoule per kilogram degree in Kelvin, 0.48 kilojoule per kilogram degree in Kelvin. And I'm going to give you the specific heat for copper. So the specific heat for copper is 0.38. So Cp for copper is 0.38 kilojoule per kilogram degree in Kelvin. I'm just going to give you the copper value, but we looked up the value in for iron in the text. You'd have to go to some other site or some other source to get the specific heat for copper. These are evaluated at 300 degrees, by the way, 300 degrees Kelvin. Okay? Okay, so we have specific heat, we have the temperatures, we have the mass. This is mass for the copper. So I'll put a C here. Okay, let's plug in. Let's see here. I have how much for the copper? 20 kilograms for the copper. 20 kilograms. The specific heat is for the copper is 0.83. I'm sorry, 38 kilojoule per kilogram degree in Kelvin. I hope it's clear that we're assuming constant specific heats when we're doing this problem. We're assuming constant specific heat. And then I have natural log of T2 over T1 for the copper. The copper ends up at the lake temperature. So T lake is the final temperature, and the lake temperature is 15 degrees C, so plus 273. Okay, and then we have the initial temperature for the copper, which is 80 degrees, so that's 273 plus 80 degrees. And let's crank this out here. Let's crank this out. Let's see here, 20 times 0.38 times natural log. And I get -1, -1.55. Let's see, what's the unit on this here? Kilograms cancel out, and I get kilojoules per degree Kelvin. So delta S from 1 to 2 for the copper. Oops, I don't know what I'm doing there, is -1.55 kilojoule per degree Kelvin. Okay? So that's the change in entropy of the copper. This should make sense because temperature is falling. Usually as temperature goes up, holding pressure constant, usually as temperature goes up, entropy goes up. Why is that true? Because to heat something up, usually you're adding heat. To raise the temperature of some system, you usually have to add heat. And when you add heat, you add entropy. So you can think about something getting hotter, meaning increase in entropy, because you're having to add heat to it to heat up. Or you're having to do work on it, and often that's shaft work or electric work, which is also irreversible. Okay? All right, so the copper entropy went down. Let's do the iron entropy. Delta S for the iron from 1 to 2. Well, that's going to be equal to the mass of the iron times the specific heat. So CV ln T2 over T1, we can put the specific heat. I guess I'll do CP here. ln T iron 2 over T iron 1. And again, this is for the iron. And let's see here. We got, how many kilograms of the stuff? 50 kilograms, as I recall. 50 kilograms. The specific heat for the iron, 0.48. 0.48 kilojoule per kilogram degree in Kelvin. Natural log, and this is the lake temperature. The final temperature for the iron is the lake temperature. So again, that's 273 plus 15 divided by 273 plus 80. Okay, so let's calculate. Temperature is falling, so again, we assume a reduction in temperature. Okay, so that's negative 4.88. And the unit on that is going to be kilojoule per degree Kelvin. So delta S for the iron from state 1 to state 2 is equal to negative 4.88 kilojoule per degree Kelvin. So the entropy went down. Now, where did the entropy go? You know that entropy can't be consumed. Well, what happened was, of course, that the iron and the copper rejected heat and therefore entropy. Rejected heat and therefore entropy. So we have Q and we have S being transferred. Heat and therefore entropy being transferred to the lake. So the lake is going to gain entropy and gain energy, and the lumps, which were hot, are going to lose energy and lose entropy. So let's calculate the entropy change for the lake. Let's do that. Let's calculate the entropy change for the lake. So I think what I'm going to do here, I'm going to write delta S for the copper and the iron over here because we're going to come back to it. Delta S iron 1 to 2 is negative 4.88 kilojoule per degree Kelvin, and delta S for the copper from 1 to 2 is negative 1.55 kilojoule per degree Kelvin. Okay, so we're going to come back to these. So I want to write them down somewhere. Okay. Now I think I'd better put up the system here. So we're looking at the lake now. So here is the lake. And here's my lump of copper and iron. Okay, so this is my iron, and this is my copper. Now I'm going to make, in the previous analysis, to calculate delta S, my system was implicitly the lump of iron and the lump of copper separately, and I calculated delta S. So the system here for the iron, when I'm calculating delta S for the iron, was the iron at temperature Ti1 going to Ti2. Okay, so this is the iron, okay, and that was my system. Now my system is the lake. So here's my system, it's the lake. Now I'm going to stamp out or punch out the iron and the lumps of copper. So my system is the water in the lake. So system is lake water. So system is the lake water. All right? Now let's see if I can calculate delta S for the lake using the equation, using the property relationship that I used for the iron and copper. So delta S for the lake from state 1 to state 2 is the mass of water in the lake. So M lake, CV, Ln, T lake 2 over T lake 1. So you might try writing this, and let's see if we can calculate change in entropy of the lake. Well, we got a bit of a problem here. I don't know how much water is in the lake. In fact, the assumption is that the lake temperature doesn't change, which means that the lake is very large compared to the lumps of copper and iron. So I don't know what this is. I have no idea what this lake water mass is. And also, the final temperature of the lake water is assumed to be the lake temperature. So this natural log here, the final temperature is the lake temperature, the initial temperature is the lake temperature. This natural log gives me ln of 1, which is 0. So this lake mass is very large, and this natural log is 0. I don't know what that product is. So I don't think this is fruitful to go down using the property relationship on the lake water. That's not very fruitful. Let's try something else. Let's try an entropy balance. So the point is, we don't really know what this produces, this quantity. M lake is very large, and Ln, the temperature change, is approaching 0 or close to 0. So this is not going to help us. So let's try the entropy balance on the lake. Let's try that instead. So let's try S balance on lake. Now what I mean by that is lake water. Okay? That's the system we have here. That's the system we have here. So I have delta S from 1 to 2 is equal to the integral of del Q over T interaction. And remember, there may be multiple heat interactions going on, so we got a summation sign there, plus S gen 1 to 2. Now, this lake is very, very large. That means that the temperature of the lake isn't changing. More than that, I'm going to draw my system. I've sort of done it here. I'm going to draw it so that the heat interactions, the heat being transferred from the copper and the iron into the lake, I'm going to draw it such that the interaction temperature, if I put a thermometer right here on the system boundary, my lake water system boundary, where Q is being transferred from the copper, if I put a thermometer right there, I'm going to get an interaction temperature equal to the lake temperature, okay? I'm going to have my lake system such that I move far enough away. There's a hot lump here, and there's cool water out here. So I'm just going to back off. I'm going to back off on my control volume and not allow the control volume to be at the surface of the copper, but just a little bit further away, such that the interaction temperature, or the temperature where the heat is transferred, is equal to the lake temperature. I'm going to do the same thing with the iron. So the interaction temperature is going to be the lake temperature. Okay? Now, what that also means is, because the temperature here is a lake temperature and the temperature here is a lake temperature, where the heat is transferred, as the heat flows into the lake water at the lake temperature, the heat is always flowing at the lake temperature. That means that it's reversible as far as the lake is concerned. If there's no temperature change as the heat disperses throughout the lake is large, it's a reservoir, so temperature is constant and is equal to the lake temperature. So if I draw the control volume the way it is, where the interaction temperatures are the lake temperatures, then as the heat flows out and distributes itself throughout the lake water, it will do it reversibly, because there's no temperature change as the heat moves around. So I'm going to make a big assumption here over in the bottom. I'm going to make a big assumption here. The big assumption is not a lot of room here. Reversible heat transfer in lake. Reversible heat transfer in lake water. And what that basically means is the interaction temperatures are the lake water temperatures. That's basically what that means, okay? So this implies reversible heat transfer. The heat enters the lake water system at the lake temperature and then disperses throughout the lake. So there's no temperature change as that heat gets dispersed throughout the lake. So that means reversible heat transfer, there's no entropy generation. Reversible heat transfer. Okay, so that term goes to 0. So all I got is this integral, del Q over T. Let's see here. There's actually two heat interactions going on. There's one going on with the copper and the iron. So two heat interactions. So this integral becomes two integrals integrating the heat transfer from the copper to the lake and the heat transfer of the iron to the lake. The interaction temperatures are always T lake. So this guy is equal to del Q over T lake, and that's for the copper, plus the integral of del Q over T lake, and that's for the iron. Two heat interactions, therefore we have two integrals. Interaction temperatures are the lake temperatures. Let's move over here. So let's write this entropy balance one more time and figure out what these integrals are. Lake temperature is 15 degrees C, so let's remember that. Lake temperature is 15 degrees C, and we're going to find the total change in entropy of the lake lump system or the universe. We're going to find that as soon as we find delta S for the lake. Okay, so delta S lake from 1 to 2 is now equal to the integral of del Q over T lake. And that's for the copper system. That's for the heat transfer from the copper system. And then we got another integral for the iron system. Now, the lake temperatures are constant as far as the integral is concerned, so we can pull them out. I get 1 over T lake, and then I'll group together these integrals. Integral del Q, and this is for the copper, 1 to 2, plus integral of del Q for the iron. Okay? Now, these are heat interactions to the lake. Remember, in the energy balance, Q is to the system. And for the entropy balance, this is added to the system, positive. So the integral of the little bit of heat transfer over the process from the copper to the lake, well, that's going to be equal Q copper, and this is going to be equal to Q iron, and that is to the lake from the copper and the iron. We need to figure out what these are. So let me write the final expression. 1 over T lake, Q iron, and Q copper. 1 to 2 plus Q iron. 1 to 2. We need to find out what these heat transfers are. What these heat transfers are from the copper and from the iron into the lake water. Well, we can do that by using the first law applied to the copper and the iron. So here's the iron. So let me write the first law. Q minus W equals delta E. And this is for the iron. I'm sorry, yeah, we're doing iron. And no change in kinetic and potential energy, let's assume. So this is delta U. There's no work going on. There's no shaft work, no electric work, no boundary work going on during the process for the iron or the copper lump. And so we simply get Q iron equals M iron C delta T from 1 to 2. Let's see here. How much do we have? We had, for the iron, we have 50 kilograms of the stuff. The specific heat for the iron, what was that? 0.45? 0.45. And the temperature change was 15 minus 80 degrees C. Okay? So let's crank that out. 50 times 0.45 times 80 minus 15. And I get minus minus 146.2 kilojoules. So we're rejecting heat from the iron, Q1 to 2. Same thing for the copper. What's the heat being rejected from the copper? Well, that's going to be Q copper equals M copper, C for the copper, delta T. So what do we have? 20 kilograms, 0.38 as I recall. Is that what I put down? 0.38. Yes, 0.38. And then we have 15 minus 80. So we have 20 times 0.38 times 15 minus 80. Negative 494 kilojoules, okay? So that's heat being rejected from the copper from state 1 to state 2. Remember, what's being rejected from the copper and the iron is being added to the H2O. So T lake is 273 plus 15 degrees C. So this will all have units of Kelvin. So I'm going to put in positive Q copper because this is heat rejection from the copper, which is being added to the lake. So this is to the lake here. So this is going to be plus 494, and this is going to be plus 1467. Okay? So 494 plus 1467, and that all has units of kilojoules. We're going to get kilojoule per degree Kelvin here. Let's see here. 494 plus 1467 divided by 288. 6.8. 6.81 kilojoule per degree Kelvin. So the change in entropy of the lake, water, using the entropy balance. So here's our lake, water. So here's our lumps. State 1 to state 2. So our lake water, that's our system, punching out the space contained by the lumps of metal. So delta S for the lake water is 6.81 kilojoule per degree Kelvin. Let's box that up. Okay? Had to go through and use the energy balance on the solids. Again, no work because there's no change in volume. Solids are incompressible. No change in kinetic and potential energies, therefore Q is equal to delta U. All right, let's calculate the change in entropy of the universe. That means everything as far as the problem is concerned. Delta S universe. What I mean by that is everything. What's the change in entropy due to this process? What's the change in entropy of the universe due to this process? Everything everywhere due to this process. Well, that's going to be equal to the change in entropy of all the systems. So change in entropy of the copper from 1 to 2. Change in entropy of the iron from 1 to 2, plus the change in entropy of the lake water, 1 to 2. So let's calculate the change in entropy of everything. My lake plus my lumps of iron and copper. Let's see here, delta S for the copper, that was negative 1.55 kilojoule per degree Kelvin. Okay, so we lost heat to cool down the copper, so entropy fell. Same thing for the iron. Negative 4.55 kilojoules per degree Kelvin. The lump of iron cooled down, so heat was transferred out of the iron, as well as entropy, so entropy fell for the iron. But the lake gains entropy because heat's being transferred. Heat's being transferred from the lumps of copper and iron into the lake water. So the lake is gaining entropy and energy due to heat transfer from the iron and the copper as they cool down. So then I got a plus 6.81 kilojoule per degree Kelvin. Let's crank that out. Let's see here. 6.81 minus 1.55 minus 4.55. And I get plus 0.71 kilojoule per degree Kelvin. So delta S of everything, or the universe. Remember the handout we had where we talked about the environment, the universe, the system. Delta S for the universe, which is delta S for the copper, the iron, and the lake all together. That's going to be equal to 0.71 kilojoule per degree Kelvin. Okay? So it's positive. Let's just think about this for a second. This process resulted in a change or an increase in entropy for everything, or the universe, as we go from state 1 to state 2. Why might entropy of the universe be increasing? Well, the reason for that is because this is an irreversible process. How do I know that this is an irreversible process for the lake and the lumps of material? Let me draw the lake and material system, and we're going to figure out the entropy generated over the process. Let's find S-gen. Let's find S-gen for the process. And that means for the lake and the iron system together. So here's my iron, and here's my copper, and here's the heat transfers. Okay? Now I'm going to make my system the whole thing. Lake and iron and copper. Now the lake is assumed, we can assume that the lake itself is not receiving any heat transfer except due to the copper and the iron. In other words, there's no heat transfer from outside the lake, iron and copper system. Okay? That's just kind of an assumption as far as the problem is concerned. So we're only looking at the lake, copper, iron system, and there's no heat transfer from outside the system into the lake or out of the lake, copper, iron system. Okay? So my system is the whole thing here. Iron, copper, and the water. Notice I don't have any dashed lines indicating that I'm excluding the copper or the iron from the system. So let's apply the entropy balance to my lake copper plus iron system. So S balance on lake plus iron plus copper system. Let's see here, delta S 1 to 2 is equal to the integral of del Q over the interaction temperature plus S gen 1 to 2. Okay? So we're assuming there's no heat interactions for the iron, lake, copper, the whole system. The whole system. So this is 0. So immediately I get S gen over the process within my lake, copper, water, iron system is equal to delta S 1 to 2. And that's my delta S for the universe. Delta S universe, which is 0.71 kilojoule per kilogram. So entropy was generated for this process. 0.71 kilojoule per degree Kelvin was generated inside my lake iron copper system somewhere over the process. S was generated. So there's an irreversible process going on here because S gen is positive. Where might it be coming from? Why is entropy being generated as the heat is transferred from these hot copper and iron lumps into my cold lake water? Well, the reason for that's obvious. This is an irreversible process. It's a heat transfer from a hot body to a cold body over a finite temperature difference. The temperatures of the lumps of iron and steel are originally, copper and iron, are originally 80 degrees, and the lake is 15 degrees. So there's a temperature difference, delta T. In other words, entropy is being generated in a thin region. A thin region around, don't want to make this squeak too much. There's a thin region around the iron and the copper. A thin region around the iron and the copper over which temperature goes from the iron and copper temperature to the lake temperature. So let me blow up the edge of one of these regions here. So let me blow up the edge of one of these regions here, this transition region. So here we have the edge of the iron. Here we have, and on the iron, so right here on the iron, the T here is T iron. And then I got out here, T lake. Out here is T lake, over here is T iron, and in between, there is a transition region in which temperature is falling. So here's temperature. Temperature starts off high, so this is T iron, and this is T lake. Temperature starts off high and falls through this transition region. Heat goes from hot to cold. So heat flows through the transition region from the hot iron to the cool lake, and entropy is being generated across this temperature jump S is being generated in this transition region, this buffer here. S is generated in buffer region here. S is generated in this buffer region. Heat is flowing from hot to cold in this buffer region, surrounding my iron and my copper as the heat flows into the lake. Okay, so let's recap this. This is an irreversible process. Heat is being transferred from two hot materials into a cool lake. We're going to get entropy generation. Where is the entropy being generated geographically? What's the source of the entropy generation? It's not in the lake water, because we've defined the system, the lake water system, such that the interaction temperature is the lake temperature. It's occurring in a transition region. The entropy generation is occurring in a transition region near the iron, in which heat is being transferred from the hot iron and copper into the cool lake water. So entropy is being generated in this buffer or transition region. All right, ladies and gentlemen, I think that's enough there. I think we've gone a little bit over time. I didn't mean to go so long. So take care, ladies and gentlemen.